Yay! All right. Okay, so the class is called Sound System Design, which we will do that eventually. But before we do that, we have to learn a little bit, or maybe even a lot, about how sound actually works, independent of sound systems. Because sound systems, in the way that we're going to sort of define them, are a relatively new, idea. We're talking like, within the last 100 years, sound systems, as we sort of understand them now, have existed. Prior to that, there was a whole lot of time that people were living on this planet and getting along just fine without sound systems, and they were relying on, some physics and stuff to make all that happen. And all of those things still exist. Like all of those rules and those physics haven't changed dramatically. Our understanding of them has evolved a good bit, but they haven't really started behaving dramatically differently, despite our slow pace at understanding it. So before we can really understand what the sound system is going to do for us, we kind of need to understand what happens if we don't even show up for work, okay? Because when we're designing a sound system, we're really plugging a gap, right? We're looking for a hole that the physics are not filling for us. And so before you can plug that hole, you have to know where that hole is, okay? So the first half of this semester, we're going to really be talking about the math and physics of how sound works, okay? So this section is really about wave propagation. There's a way that you can look at sound where it would behave like something you would describe as a wave. So we're going to talk about that. So the first thing the first property of a sound wave you need to understand is that it travels at a somewhat predictable speed. Okay, it travels approximately. The textbooks will tell you 1,130 feet per second, or for the metric inclined, that would be 344 meters per second. However, for our purposes, we're going to do this in feet, not because I have anything against metric. Metric is great, and I use it when it's appropriate. But the math for sound is actually easier if we do it in feet. Okay, it's quite a bit easier. Not easier just because it's like, oh, stupid Americans don't know metric. It's like, no, it's demonstrably easier because 1130 feet per second is really, really close to 1,000 feet per second. And in reality, I've actually never seen sound travel 1,130 feet per second. I've always seen it travel slower than that. Here in Winston-Salem, North Carolina, it's about 1,050 feet per second. Because I measured it one time, and that's about what it is, which is much closer to 1,000 than 1,130. And if you do 1,000 feet per second, that's an awfully round number that is really easy to do math on. Okay, much easier to do math on than 344. Okay, so there will be some times when I say, okay, let's figure this one out in our head. And when I say, let's figure this one out in our head, I mean, let's use that nice round number, 1,000 feet per second. Because we can do that we can do math on 1,000 in our head. If I say, let's do this one with a calculator, then you're going to use 1,130 feet per second for the speed of sound, okay? So I said it's kind of a moving target. And the reason is that there are a few sort of environmental things that affect how fast sound travels. One is temperature. So sound actually travels faster in warm air than it does in cool air. So depending on the temperature, it will, the speed of sound will change. So as the room gets warmer, sound travels faster. As the room gets colder, sound travels slower. And if there's more than one temperature happening in your room at one time, which is possible, things start getting really weird, which we'll talk about in a little bit. Okay. Pressure, have an impact on the speed of sound. What would affect the pressure in the air? Altitude, right? So that's why I say here in Winston-Salem, North Carolina, it is this, right? If you go to a different altitude, it would change. The other thing is humidity also impacts the speed of sound. So that's something to think about. There are a lot of things that can affect the speed of sound. So even though we kind of know how fast it travels, it's not a fixed value, which is important to remember. So.
For humidity,
yeah.
if it's more humid, does it travel faster? slower?
I don't know, actually.
Okay.
Off the top of my head, I can't remember. Yes?
So how did they decide? Is it? I'm guessing the pressure is like 1 atmosphere, and how did they decide like what humidity to say this is the speed of sound?
No idea.
I bet it was some form of physicists assume perfect conditions.
Yeah, usually what happens is, somebody does some research and samples a lot of different things and comes up with an average or something. Or there's a lot of that kind of stuff we're going to talk about where it's like, okay, this is how we understand this, and we understand it because the first person to really like put this into words said it this way, and so everyone just sort of like followed that person's lead, even though we realized later that it worked slightly differently. There was this guy named Sabine that said an awful lot about how sound reflects around a room, and by now we understand it much more than he ever did, and a lot of his writings are we don't even really want to use them anymore because they've lost a whole lot of meaning, but we still use them because he was the first person to talk about it, and so he defined the vocabulary. It's very weird. So all right, so that's velocity, that's speed, right? Let's take a look at some of the other properties. So we know that a sound wave travels a somewhat predictable speed, but there is some other things that happen. So sound is actually air. Okay, you can't have sound if you don't have air. And the way that the air works with the sound is that even though we can't see it, I'm told that air is actually made up of little molecules that we can't see, or we can't see easily. And those air molecules are kind of like connected to each other in some sort of elastic way. They have like a resting state of where they want to be, but like anything elastic, you could like stretch them apart and you could squish them back together, and they would sort of bounce. If you squish them together, they'd sort of try to bounce back to wherever they're comfortable. If you try to stretch them apart, they would then bounce back to where they're comfortable. Okay, and so what happens with sound is when something tries to squish those air molecules together and stretch them apart, and if it does that, fast enough for a long enough period of time, it will excite your ear, and something in your ear will start moving sympathetically to that squishing together and stretching apart. And that sends impulses to your brain that makes you hear something sound. So what's actually happening in the air is just air molecules pushing together and stretching apart. And you happen to have a tool inside of your head that can convert that air moving like this into something that it's a sensation that you interpret as sound. That we call the squishing together of the air compression, and the stretching apart of the air rarefaction. And depending on how fast that goes, that dictates pitch or frequency. Yeah?
On the sine wave you have it there, would the peak be compression, and then as it's going down be the refraction, and then the apex to the bottom, and then the compression?
Yeah. Compression, refraction,
Okay.
resting state.
Gotcha.
Okay? So we use this term a cycle in reference to sound. And a cycle is when we do one full compression, one full refraction, and then back to whatever that zero resting state is. That's one cycle. The number of times or cycles that you have in a second is what we call frequency, which we measure in hertz, cycles per second. And you have to have at least, the textbooks will tell you, at least 20 cycles in a second in order for your brain system to interpret that as sound. Although, in my experience, it's more like 50 to 40. I mean, much lower than 40 or so, and you're not hearing a whole lot. And you can go as much as the textbooks say 20,000 hertz, although in practice it's closer to 16,000 hertz. It's very few people I've met that can hear 20,000 hertz. And it's not that above 20,000 hertz, that there aren't, air is not being excited at higher rates than that. It's just that our mechanism to interpret it is not capable of doing anything with that information. There are other creatures on this planet that can do something with that information. We just cannot. So this sort of range of 20 hertz to 20,000 hertz that you see all the time in spec sheets and textbooks and everything, just know that that's it's not really that's not a hard and fast rule. I mean, it's a moving target. If we have time this year, I'm going to give you all hearing tests, and we're going to find out what your actual hearing is like. And it'll all be different. Everyone will be different. What's that? Not really, because it has no error correction in it, which is problematic, because it's all dependent on like how fast you click your mouse and all, and you know, a proper hearing test actually would test you would take you up to certain points, and it's really not about the range, it's about, you know, sensitivity. So a true hearing test is about sensitivity, and it's more about they give you something and then they see if you respond to it, and if you do, they go quieter than that, and if you don't respond to that, then they go back to the thing that you responded to last time, see if you respond to it again. If you don't, then they go back. Right there, there's a lot of they require you to sort of like have 2 or 3 yes responses to something before they'll say, okay, yeah, you definitely heard that, because there's some times where you'll trick yourself into hearing things. Because, again, sound doesn't actually really exist. It's a sensation that you're interpreting in your brain. So your brain can sometimes play tricks on you. Yeah, sound doesn't actually exist. It's just air moving around. Okay. So something that's really, really important, super critically, absolutely, totally important to understand, is that this is not what sound looks like. This is not a picture of a sound wave.
Okay, this is a very. Did you ever see the Magic School Bus episode where they went into the haunted house and there were sound waves?
No.
Okay, because you should watch it and tell us how accurate that is, because I think it's pretty accurate.
So here's the problem. Here's what this actually is. This is not a picture of a sound wave. This is a graph of air pressure amplitude. Okay? It is a graph, not a picture. A graph of air pressure amplitude. The sound wave doesn't actually look like this. The sound wave is not moving up and down in the air. It doesn't do that. Okay? Sound is what's called a longitudinal wave. And I will attempt to demonstrate that here with this thing from my book. Let's see if it works. Oh, yeah, it works. Okay, good. So, so this is what we would call a transverse wave. And we tend to graph sound waves as transverse because it's really difficult to graph a longitudinal wave. It took us, when we were doing the book, a long time to figure out how to do it. And then we figured it out, and everybody's copied us, and I was so mad. D&B copied us. I saw in Chris's slide, and he's like, copied me. What's that? Yeah, he did, probably. So this is a transverse wave, you know, and there's lots of ways you can make transverse wave. It's not that, you know, it's not that transverse waves don't actually exist. They do. This is an example of someone making one out of like a rope or something. You can do this, but it's just that sound doesn't do this. Okay. And the idea behind a transverse wave is that the direction of motion is perpendicular to the direction of propagation. So the energy propagates in the opposite direction, or, well, a perpendicular direction to the actual displacement. So here we're displacing the rope vertically up and down, but the energy is actually propagating horizontally. Okay? So that's transverse wave. Sound, on the other hand, is longitudinal. So this is what we came up with. So imagine, you know, these are the air molecule dots that we can't see. They're everywhere, by the way. They're not just in a column, but the column makes it easier for us to diagram. So the idea here is that in a longitudinal wave, the direction of motion is parallel to the direction of propagation. So we are pushing these air molecules together and stretching them apart, and the energy actually propagates in that same direction. Okay? So what's happening here is we've got a little loudspeaker that's like pushing on the air, and that pushes on the air next to it, which pushes on the air next to it, which pushes on the air next to it, until eventually it pushes against a bit of air that's right up against your eardrum, and that bit of air pushes on your eardrum, and your eardrum then does the thing. Okay? That make sense? Yes? Okay. So, again, so this is not a picture of sine wave. I kid you not. And this is we laugh, but this is not a widely understood concept. Actually, this is a very widely misunderstood concept, because we spend a lot of time looking at these little graphs, and we start thinking that this is what sound does, and that's not what it does. If you think that this is what sound does, then you could fall victim to some really dangerous misconceptions, like it's possible to duck the wave, right? And you can't. You can't. that sound wave is coming at you, and you can't duck it. I mean, I had a salesperson at a Best Buy or something one time tell me that you got to be really careful where you put your subwoofer in the room, because the wavelengths are so big on that thing that if you put it in the wrong place, the sound will just go right over your head. And it's like, no, that's not exactly how it works.
Does he think that you missed the first wavelength?
Well, what he didn't understand was the concept of standing waves, which we're going to play with in a minute here. And that is a concern, but it's not happening for the reason that he thought it was happening. It's happening for a different reason, but it's not because you happen to be sitting underneath the peak or something, right? No, I just was like, whatever. Okay, so here's another example here. So I think in this one I'm going to connect these properties of waves in here. So here's a slightly larger picture of the air molecules that we can't see. They're everywhere, and that you see how they're sort of like they're hovering, right? They're ready to move, but this is kind of where they want to live, right? We're going to simplify it by just focusing on one little column of that, and we're going to create this thing. And this is the compression, okay? And the refraction is that part. You see how that's moving? Now, how does that connect to the graph? This is now the graph, okay? So this is the thing that we graph, is this sort of like transverse wave, because that's easier to draw on anything. It's much harder to draw a bunch of dots moving.
Wait, I thought you said that compression occurs on peak and.
No, you said that.
Oh.
I said that's a peak and that's a refraction.
Okay. So it'll need the peaks or compression, not the drops.
Right. Because remember, it's a graph of air pressure amplitude. So the air pressure is either really high because it's squished together, or it's low because it was stretched apart. Okay? And then you let go, and it goes back to that zero spot. Okay? So when we draw that little wave graph, that sine wave, transverse wave graph, I want you to just keep in mind that is a graph, not a picture. What you're seeing up above here is more like what's actually happening. Okay? Even this is somewhat abstract, but is a closer visualization to drawing this wave. That make sense? Any other questions about this? Super important. Because this is one of the biggest problems we have in sound, is that you can't see it. And that comes into play in a lot of ways, especially with people that you collaborate with that just can't understand anything that they can't see. And so not being able to see it causes us a whole lot of problems, not the least of which is it travels really slow, relatively speaking, to other things that we can see. Or basically everything that we can see. Sound travels significantly slower than light. And light is what allows us to see everything else in the universe. And sound travels so much slower than that. But because we can't see it, it's really hard to visualize how slow it's actually moving. And that makes it really hard to wrap your head around how to possibly control it. Because you can observe something visually much faster than you can hear something. So it causes us, it's a big problem, actually. Just to try to drive this concept home, here's another example of converting a longitudinal wave to a transverse wave. So here I've got a spring with a little weight on it, and I'm going to put a little pencil on the weight and move a piece of paper underneath of it. Right? And so here I'm converting one into another. See that? See how that the green line is actually a graph of what the weight on the end of the spring was doing? It's just a graph. Okay. Have I sufficiently driven that concept home? We get it now? Okay. All right. You can take the quiz yourself later. All right. So there's another concept. We talked about speed of sound, velocity. We've talked about frequency. Now we're going to talk about wavelength. So if sound travels a somewhat predictable speed, and if sound happens when compressions and refractions occur within a short enough period of time, then there is a predictable distance by which a compression happens, or a compression has completed. Okay? So just as we noticed as that wave was crawling across the screen, there was a measurable distance between the two compressions, right? That you could measure that with a ruler. Okay? And it's because of the somewhat predictable speed of sound. So the distance that sound travels before a full cycle has completed, that is called the wavelength. The wavelength is a really major moving target. We tend to sort of talk about it as in absolute terms, like saying that, 1 kilohertz is a 1 foot wavelength. And that's mostly true, but it's hardly ever actually true. It's almost always a little bit more or a little bit less than 1 foot. But it's helpful in the sense that we cannot see sound. This is a helpful way to visualize it. If we can kind of wrap our heads around kind of wavelengths and how that works, that helps us better understand how we could control the sound if we can have some sort of visual idea of how big the thing is that we're trying to control. You can figure out wavelength by taking the speed of sound and dividing it by the frequency. And I don't know if you learned, I learned these little triangles when I was in high school, which I found were very helpful to me, because we will do a lot of conversions between frequency to wavelength and frequency and wavelength into speed of sound and so on and so forth. So this little triangle helps me to do that algebra. So for example, if I want to know wavelength, I would do speed of sound divided by frequency. If I want to know frequency, I would do speed of sound divided by wavelength. If I want to know speed of sound, I multiply wavelength by frequency. See how that works? Just a helpful little shortcut that makes me not have to think as hard. Okay? Yes. So I'll tell you a story. Anyone in here uncomfortable with math? It's okay. I'm uncomfortable with math. Am I the only one? I'm uncomfortable with math. Yeah. So it's okay. It's nothing to be ashamed of. I'm very uncomfortable with math. I got into theater because I thought I wouldn't have to do math. Totally did not work out for me. But let's try it anyway. So,
Even went mathier than some sound designers will ever go.
yeah, I really fell down the rabbit hole. But all right, so here's an example. We're going to do this in our head. So no calculators, just like let's try it. What is the wavelength of 20 hertz? Well, if I want to know wavelength, that's this one here, I do speed of sound divided by frequency. So I'm going to say wavelength is equal to 1,000 feet per second, right? Because we're doing it in our head, we're going to do 1,000. It's easier that way. Divided by 20 hertz. So what's 1,000 divided by 20? 50, right? So that would be 50 what? Feet. Feet, because it's 1,000 feet per second. Okay? That makes sense? We did it. Let's see if I can clear that out. All right. Let's try another one. What is the frequency of a sound that has a 10-foot wavelength? Okay, so in this case, I want to know frequency. So I'm going to do speed of sound, which is 1,000. Oops, not. Put an extra 1 there. Sorry. 1,000 divided by 10-foot wavelength, and we get 100 what? Hertz, yes. Hertz, cycles per second. So far, so good? Okay. What is the wavelength of 1 kilohertz? Well, I just told it to you. Everybody remember what it was? Well, yeah, so let's just prove it. 1,000 feet per second divided by 1,000 hertz. 1 foot. Right? Easy. You see why we do this in feet now, rather than immediate. It literally makes the math easier. How about this one? Wavelength of 250 hertz. So this would be 1,000 feet per second divided by 250 for what? Feet. So 250 hertz is a 4-foot wavelength. So you can start to visualize these things, right? You could really quickly in your head kind of figure out how big this thing is. And that can help you in ways that will make sense later. But being able to sort of understand and visualize how big is this sound that I'm trying to like do something to right now. And if you realize, oh, it's that big, you realize, okay, I need something that's at least that big in order to stop it or impede it or something, right? So, one of these little panels, for example, is not going to do anything to 100 hertz. Why? Because 100 hertz has a wavelength of
1 foot. No.
10 feet,
10 feet.
right? So if I wanted to affect 100 hertz at all, I would need a panel that was at least 10 feet in some dimension, right?
So what about the panels that are technically 10 feet but have a little bit of space in between? Does it do it?
Oh, no, it totally does. The space helps, right? That creates a volume that helps capture that 10-foot wavelength.
Would it be better if you're trying to do that to have no treatment at all? Then, if it's not going to do it, like one panel of those isn't going to do anything?
Well, but it won't do anything for 100 hertz, but it will do something for, 250 hertz and above, right? Because that's 4 feet wide. Okay, what is the frequency of a 5-foot wavelength? So that would be 1,000 feet per second divided by 5. 200 hertz. Very good. What's that? It's not. Yeah, we haven't got to the hard stuff yet. We're warming up here. Okay, we won't get to the hard stuff for a couple more weeks. But okay, here's a little bit gotcha one. Be careful. Careful with this one. So, what is the frequency of a sound that takes 50 milliseconds to complete one cycle?
Okay, wait, so cycles per second.
So there's 1,000 milliseconds a second.
Yeah, so that's the first question is how many milliseconds are there in a second? 1,000, right? Okay.
That'd be 5,000.
So if sound travels 1,000 feet per second, then I divide that by 1,000 to get milliseconds, right? So now it would be 1 foot per millisecond, right? Okay. So if I say 50 milliseconds, then 50 milliseconds is otherwise known as 50 feet, right? Yeah? So now that I know that, I should be able to figure this out now. So now I can do 1,000. So this is our wavelength now, right? 1,000 divided by 50. And I get 20 hertz, right? All right. Here's the slight catch, though. It's not actually 50 feet, because I said do this with a calculator. And when we do it with a calculator, we use a slightly different speed of sound. So I want you to remember, really, just glance at this, understand how we figured this out, because we're now going to do it a slightly more complicated way. You ready?
Yeah.
Okay. So, and I just realized that I don't think I installed pcalc on this new computer. So we may have to use the regular calculator. Let me see if I did or not. That's okay. We'll use the regular calculator for now. I don't need pcalc is not going to help me for this stuff. Okay. So so I'm looking for frequency that takes 50 milliseconds to complete one cycle. Okay, so we first need to find out how many feet per millisecond, right?
So are we doing it at the speed instantaneous or
The speed according to the textbook, which is 1,130 feet per second, right?
Yeah.
That's the speed of sound according to the book. So what do we need to do to that to get?
Divide that by 1,000.
Yeah, so we'll divide that by 1,000. we get 1.13. So it's 1.13 feet per millisecond.
So now we just have to do 1,000 divided by 1.13.
You each have to do 1.5.
Well, yeah, so that's how many feet per millisecond. So if we've got 50, wavelength that's 50 milliseconds, we need to take 1.13, multiply by 50, and we get 56.5. So yeah, now what we're going to do, I'm going to put that in my, oops. I can't see, this is not pCalc, I can't see it. Okay. So we're going to do 1,130 feet per second divided by, there it is, 56.5, and I get 20. So it's still 20.
Yeah, because it's still just a rough estimate. So the
Yeah,
total number
it's pretty close. And that's the other thing you'll learn about this math is, like in sound, close counts. You know, we're abstracting our math so much that, you know, you can be technically wrong but still right. Still get the same answer. Was that? None of this actually matters. That's actually that's true. I mean, like, really, nothing that we do actually matters. They did theater for thousands of years without us. We could not show up and they could still do it, right?
I was going to say, it was probably better.
Yeah, in some ways it was probably better, but at our best, I think we improved the situation a little bit. All right. Okay, here's another one. Wavelength of 20 kilohertz. And we're going to do that with our calculator as well. So this would be 1,130 feet per second. Oops. 1, 1, 1, 3, 0. Divided by 20 kilohertz, right? So that would be 20 plus 3 zeros. 1, 2, 3. I get 0.0565 feet. So 20,000 hertz is 0.0565 feet. It's like teeny. Okay? It's like half of your pinky. Make sense? Easy to stop, right? Something this big, no problem. We can stop 20 kilohertz easily. Stopping 100 hertz, that's another thing, right? Okay. Let's see what our next one is here. Okay, so frequency, we'll have a 7-foot wavelength. So 1,130 feet per second divided by 7. We get 161.43 hertz. I usually prefer to round to 2 decimal places for the frequency, just because there's not a whole lot of useful information after that as far as sound is concerned. So 7-foot wavelength is 161.42 or 43 hertz. Yeah? Make sense? Let's try another one. How about 3 kilohertz? 1,130 feet per second divided by 3,000. That is 0.38 feet. Okay, so like a third of a foot. 4 inches. Okay. Oops. Not that one, not that one, not that one. Here we go. Okay, so this one is wavelength of 300 hertz, 1,130 feet per second, divided by 300, 3.77 feet. Okay, so that panel would have a fighting chance of absorbing 300 hertz. Could probably do it. Maybe not very well, but it could do it. What else we got here? Okay, frequency 3-inch wavelength. So this is the sequence of threes. Okay, so we did 3,000 hertz. We did 300 hertz. 3 inches. How do we do inches?
Multiply by 12.
Yeah.
Wait. Divide by 12.
So let's do this the long way. This is how I have to think about this stuff. I have to think about it the long way because, I'm math challenged. But I would think about this in terms of, okay, how many feet is 1 inch? So I could say 1 foot divided by 12, and I get 0.083. Okay, so 1 inch is 0.083 feet. Okay, so if I've got 3 of those, because I said 3 inches, I could take that, multiply that by 3. So that's 0.25 feet. 3 inches is 0.25 feet. Now, yes, for those of you who are not as mathematically challenged as me, realize there's a shortcut there, which is you could just do 3 divided by 12, and you get the same thing. Okay? So that's your shortcut. Is if I give you inches and you got to get it to feet, just divide it by 12 and you'll get it. Okay? So it's 0.25. So same process now. 1,130 feet per second divided by 0.25. And we get 4,520 hertz. We could also call that 4.52 kilohertz. Okay? Either way is acceptable. We tend to start doing kilohertz once you get in this kind of range because we're sound people. We don't tend to like numbers that are bigger than 3. So we're always trying to collapse things down into smaller numbers. Everything we do in sound is we're trying to figure out how to make big numbers into small numbers because we don't like big numbers. Okay? Because our big numbers are impossibly big. If we actually use the real big numbers, we'll talk about this in a few weeks, but the difference between the quietest thing that we can perceive and the loudest thing that our ears can tolerate is like 1 trillion. So that's a lot of zeros, and we don't like to deal with those kind of big numbers. So we've come up with all kinds of ways to make the numbers smaller. Okay, I got one more of these, looks like. So it's a riff on the other one before, which is what is the frequency of a sound that takes 3 milliseconds to complete a cycle? Yeah, but with calculator, we need to be doing 1,130 feet per second. Right? So we'll do this the long way, and then I'll teach you the shortcut. So we can do 1,130 feet per second divided by 1,000 milliseconds, and we get 1.13 feet per millisecond. So sound travels 1.13 feet per millisecond. I have 3 of those milliseconds, so I can multiply that by 3, and I get 3.39. So now I could do 1,130 feet per second divided by, oh, hang on. What was the number again? 1,000. My touch screen is not quite as touchy right now. Divided by, what was it? 3.39. Okay. I did 1,300? Yeah. 1,130 divided by 3.39. There we go. Okay, 333.33. Okay, so what's the shortcut? Well, you can just take 3 milliseconds, divide that by 1.13. And then you don't get exactly the same thing. Actually, we should, though. We need to multiply that. So 3 times 1.13. And there's our 3.39. So that 1.13 is sort of your shortcut. If you have milliseconds and you want to go to feet, you multiply that number by 1.13. If you have feet and you want to go to milliseconds, you divide that number by 1.13. The way that you know this is that 1,130 feet per second, the distance is always a higher value, or almost always a higher value than the time. So if you're going from time to distance, you're looking for a bigger number. If you're going from distance to time, you're looking for a smaller number. So multiplying would give you a bigger number. Dividing would give you a smaller number. Okay? So remember that, 1.13, that's your magic number. And you just have to decide whether to multiply or divide whatever you're looking at by that number, and you'll get what you need. And you'd still get the 3.33. Okay, how we doing? 11 a.m. We can keep going. Everybody okay? Have I left anybody in the dust yet? It's okay. You can. All right. All right. Let's see what else we can pull off here. So we're going to talk about resonance now. So the way that resonance is the way that sound gets loud. Okay? So the way that the little ear brain tool that we have interprets sound is like the extent to which that eardrum gets like exerted determines how loud things are, okay? Or how loud we perceive things to be. And so that directly correlates to that degree to which the air molecules are compressed and refracted, right? But you can actually use physics to your advantage to get that compression to be more. And the idea there is if we know how big a sound is, a certain wave is, then there is a physical dimension or physical space where it would fit very nicely, right? So something that has a 4-foot wavelength, for example, would fit very nicely inside of an object that also was 4 feet, like an absorption panel, or a hallway, or a room, or a doghouse, or whatever, right? So a sound that has a wavelength of 4 feet is going to fit really nicely inside of an object that is some multiple of 4 feet. Yeah? That's the basic concept here. And if it fits really well in there, then it kind of throws a little party. And suddenly that amplitude gets higher and higher. It like feeds off of itself when it fits inside of that spot. And that's called resonance, when it suddenly like starts regenerating on top of itself because it fits so well in this physical space that it's sitting in. And there's lots of different physical spaces that the sound can sit in. One is this is an example of a string. Now, what that's fine, but what's real life like? Where do we make sound fit in strings? In what situations in real life do we make sound fit inside of strings?
You mean like cable, guitar?
Yeah, like musical instruments, right? There's lots of musical instruments that have strings, right? And we vibrate the strings, and the strings vibrating make sound that we can hear, right? So, yeah, I've made some of those videos. So yeah, the sound can fit inside of the string, and that's really important. But it doesn't fit the way you think it fits, actually. It turns out that the length of the string is going to actually be half of the wavelength of the sound that's going to fit really nicely in there. And the reason is, if you understand, again, if you don't get too worked up about this graph of air pressure amplitude, this is where if you misunderstand that, you'll misunderstand how string resonance works. What's really happening is air is either being compressed or refracted, right? It's not actually moving up and down. And therefore, you don't actually have to have the full length of string, to be the same thing as the wavelength in order to get a full compression and refraction, right? Because you can pull the string up, and there's a compression, pull the string down, and there's a refraction. You just do that fast enough, and you get a sound. Okay? So the length of string that will resonate a particular frequency, that length is going to be half the wavelength of the frequency that it resonates. So, or another way of expressing it is that the resonant frequency of a given string, that frequency will have a wavelength that is twice as long as the string.
Will you say those both again so I can write them down? Or just one of them?
The resonant frequency of a string, in other words, the frequency that will resonate when you pluck that string, is going to have a wavelength that is twice as long as the length of the string.
So what determines that, I guess?
What do you mean, what determines that?
Like, if I have a piece of string that's, 2 feet long,
Yeah.
why would it come out as a wavelength that's 4 feet?
Well, because remember, sound is compression, refraction happening fast enough.
Oh, is it just because it's going clean
Compression, refraction, right? So I can either swing the string up or I can swing the string down.
Yeah.
and I'm doing compression, refraction. So I can do a full compression with half the length, the wavelength, right? Compression, refraction. So I don't need, now the whole wave kind of continues this way, right? If you were to continue the graph, it would do that. But in reality, sound takes time to happen. We can draw a picture of a sound wave and look at it in an instant and have it be there. But in reality, it takes time for that to happen. That is not all happening at the same time, right? So the string is not vibrating the whole thing all at the same time. It's always vibrating a very small part of it at any point in time, okay? It just so happens that because sound moves so slow, our sensitivity to it is also very slow. And so we don't really start registering that anything's happened until a lot of things have happened, like thousands of things have happened. It's not until thousands of vibrations of the string that we actually realize that, oh, something happened.
So now, like the guitar strings, you have usually the thicker the string, the more or the lower the.
Yeah, so that's where the example falls apart a little bit, because now you're talking about mass and tension and stuff like that, which also affect this. So we're pretending that those problems don't exist for purposes of our discussion right now. But all that really does is change the effective length of the string.
Oh, okay.
Right? So you change the mass and or the tension, and you're changing the effective
The
length.
string that's this long and like this
Yeah.
long versus the string that's
Exactly.
like
Yeah. Okay. But fundamentally, the science is the length determines the resonance. Okay. So it turns out, though, that more than one frequency could resonate in the same length of string. It's just, so when we say what frequency will resonate, I was really talking about what we call the fundamental resonant frequency, or the lowest frequency that would resonate in that string. And there's a whole bunch of other frequencies that would also resonate. So the fundamental is this first one, right, where the wavelength is actually twice as long as the string. But there's a frequency that is an octave above that, double that frequency, that would also fit. Because you could also vibrate that string twice as fast, and you could get a compression, refraction in each cycle, right? So you could get an octave above that to happen. You could go 3 times as fast as the fundamental and get another frequency that would also fit. You could go 4 times as fast as the fundamental and get another frequency that would fit. You can keep going. And you could really do that forever. So this is how musical instruments work, right? What makes a violin sound different from a guitar is that pattern of frequencies. You pluck that string, you're not just getting one frequency. Yes, you could say, well, I've tuned that to E, right? But you're not just hearing the frequency, the fundamental frequency of E. You're hearing infinite other frequencies that come along with it that shape ultimately what that sounds like. And that's how you tell the difference between E on a guitar and E on a violin. Okay, is that pattern of other frequencies that also just happen to fit at the same time. Okay, and the amplitudes are different and all that kind of stuff. So an important thing I did to keep in mind here is I'm talking about a string that is fixed on each end, right? So both, not one end isn't flapping in the breeze, right? So both of them are attached. That's when this happens. You disconnect one end of it and the rules change a little bit, as you'll see in a moment. Is everybody with me so far? Have I lost anybody yet? We're okay? Okay. So sound can also resonate inside of volumes of air. Okay? So boxes and pipes and...
like when you blow into a bottle.
Sure. Okay. So there is some science behind that as well. In this case, it's sort of like it depends on what's actually going to happen here. It depends on if you've got both ends open, then it behaves really similarly to the string, in the sense that that fundamental frequency that's going to resonate in a pipe that's open at both ends, that frequency is going to have a wavelength twice as long as the length of the pipe. Okay? So it behaves just like the string in a sense of resonance. Okay? However, if you close one end of the pipe, block it off, then it will resonate a lower frequency. So now the lowest resonant frequency is going to have a wavelength that is 4 times as long as the pipe. Okay? Which is kind of cool. Okay. Let me see if I can give you an example of this. So think about anybody ever try to like put a subwoofer in your car?
Tried? Question mark.
Okay.
He succeeded.
Or been in a car that somebody had tried to put a subwoofer into? Okay. Right. Yeah. So what frequencies do subwoofers tend to produce generally?
Like 40 to 90.
Yeah, really low frequencies, right? So let's say I don't know. Let's say 50 hertz. Okay. What's the wavelength of 50 hertz? We did it a minute ago. About 20 feet. Okay. So if you are in your car and you got the subwoofer somewhere in there, and you got all the doors and windows closed, you are essentially sitting inside of a pipe that is closed at both ends. Okay? So, which means the volume of air, that there would have to be a distance between two surfaces somewhere in your car that was at least 10 feet in order for 50 hertz to resonate inside of there. Most cars you drive around probably aren't that big inside. Probably not 10 feet, which is why subwoofers actually don't work very well in cars. And most people that have subwoofers in their cars find they have to like crack the window open in order. There's a reason. If you crack the window open, what happens? You have now opened one end of the pipe and closed the other end of the pipe, and now you only need 5 feet in order to resonate 50 hertz. Okay? Ta-da! But that's the other reason why if you pull up next to somebody in their car and they've got all their windows closed, you hear their subwoofer like crazy. Why? Because that subwoofer is trying to make sound, can't make the sound inside the car, so it finds a bigger volume of air somewhere else, which happens to be outside of the car, where it can actually do the thing. Okay? So it finds its way out into, the open air, and it is much louder outside of the car than it is inside of the car because it can't resonate inside of the car. It's not big enough space. Okay? But the take-home message here is open at one end, closed at the other end. The fundamental frequency is going to have a wavelength that is 4 times as long as that pipe. Okay? Okay, let's try a couple of these and then we'll stop. So what is the lowest frequency that will resonate in a 1-foot tube that is closed at one end? We're going to do this in our head. So if it is 1 foot closed at one end, then this frequency is going to have a wavelength that is 4 times as long as that pipe, right? It's going to be 4 feet, right? So it's actually a 4-foot wavelength, right? So if we know that, then we can say, all right, the speed of sound is 1,000 feet per second divided by the 4-foot wavelength, and we get 250 hertz. See how this works? There you go. That makes sense? Yeah. Okay. All right, what is the wavelength on the string of the fundamental resonant frequency of a 2-foot piano string? So piano string, the string is attached on each end. So I'm just looking for the wavelength. I'm not looking for the frequency because actually the frequency is kind of complicated on a piano because of mass, right? So I'm just looking for the wavelength. What would the wavelength be? 4 feet, yeah. Right? Fundamental resonant frequency of a closed 10-foot long hallway. Okay? So a hallway, all the doors are closed. What is the resonant frequency? Well, that I don't know, but the frequency is going to have a wavelength that is twice as long as that. All the way closed, like all the doors are closed. Or a pipe that's closed. Right. Yeah, so actually, I didn't say this part, but pipe open at both ends or closed at both ends, same thing. Functionally, same thing. Okay? Yeah. Yeah. In this case, it's 2, though, because I'm saying totally closed. Totally closed hallway, so it would be 10 times 2, so we're talking about 20 feet, right? Fundamental frequency would then be 1,000 divided by 20, 50 hertz. We just did that one, right? That's another example of the car. Okay. All right, we'll stop. We'll do the calculator ones on Friday. Any questions?
You're using, at least in the last question, you used fundamental frequency of a Hall type. So
Yeah.
I guess that terminology just confused me because I think of fundamental frequency as something that something produces, not as something that a space has.
Spaces have fundamental resonant frequencies.
Fundamental frequency would be length from end to end.
Yeah.
Something that's closed up.
Yep. Okay, other questions?
Wait, what if we had a bad idea for a pumpkin contest last year? That is find the resonant frequency of a pumpkin and blow it up.
Yeah.
Do you think that's possible?
You could break
You'd have to make an awful lot of amplitude, but sure.
Okay. Because we just didn't know how to go about it, but we loved the idea.
The problem you'd run into is the density of the rind or whatever, because you'd have to factor that into your equation, and you would need an awful lot of amplitude. Like you would need whatever the amplitude would be required to displace it that far would have to that amplitude would have to be like of a loudspeaker driver. It would have to exert farther than the thickness of the rind, and then it would maybe do it. Maybe. But you'd also have to perfectly seal the pumpkin. And how do you perfectly seal it after you've cut it open and gutted it and put a speaker inside of it?
You have to spray it or
Yeah, you just
Dip it in resin.
resin.
Yeah, it'd be tricky. I mean, theoretically possible, but tricky.
So for the hallway one,
Yeah.
would material affect?
Absolutely, yeah.
Okay.
Yeah, I mean, there's a whole lot of variables we're not talking about yet.
Obviously a difference between resonance and reverb, but it is.
Yes, those are not the same thing at all. They're not even close to the same thing.
Then how does
Not the same thing.
Okay. We know that there's a difference.
Yeah.
No, but like they're not even comparable.
Okay, but then how does material affect resonance the same way that material affects reverb?
It affects it, but not in the same way. No.
Got it.
They're not even related. I'm just gonna stop talking.
Yeah. Yeah, they're not the same thing at all. Okay, other questions?
So it just says reading Wavelength chapter 1. Do we just comment our faults on that for the next class?
Do you do what?
The reading.
No, you just read that if you want to. I'm not gonna test you on the reading. Yes. It's just that, if you don't like the way I said it, you can read and see what that guy said, and maybe he explains it in a different way than I did. It makes more sense to you.
Maybe you stole your diagram.
More likely I stole his, but